when do we get a gas? Well, if we look at a solid, we have all of these really close particles. These particles are held in place by their intermolecular forces, and they are rigid. They have a very fixed shape, they have a very fixed volume. And while their particles might vibrate a little bit, they're not actually able to move around each other. They are fixed in place. Compare that to a liquid. The molecules will have a fixed volume, so they'll all stay under this water line, but they're going to be able to move around each other. So they're a little more spread out and they're able to move past each other. They still aren't very spread out. They're going to be very close to each other. And because of that, they're able to slide around each other. But a liquid is generally incompressible. If you try to take a liquid and push it down to make it take less volume, you're not going to be able to, because there still isn't very much space between the molecules. What makes a gas different is that in a gas, we have added enough energy to not only overcome the bonds that are holding these in rigid place so that they can move around each other, we've overcome everything that keeps these molecules near each other. So in a liquid, the intermolecular forces are still holding these molecules close to each other. But in a gas, they're not. There's not enough energy in that intermolecular force to hold these particles together, and they just fly apart. So in a gas, really, our particles are all over the place, and we have a lot of empty space. So what are the factors that will affect the properties of a gas? Well, it's really not going to depend so much on the physical properties and the chemical compound anymore. In a solid, all of our properties really depend on what kind of intermolecular forces do we have, and what kind of bonds do we have, and what specific elements are there in place. In a liquid, it's the same thing. In fact, polarity, hydrogen bonding, those come into play so frequently just in a liquid's ability to dissolve or not dissolve something, or how easily it's able to keep itself fit in the same shape, in the same state, or if it's going to be volatile or reactive or something like that. Well, in a gas, the element only really affects the reactivity, the chemical properties, how that molecule is going to interact with other molecules. It doesn't really impact the physical features anymore. The physical features of a gas are generally the same regardless of chemical compound. Now that's generally the case. We're not really going to look at any exceptions, so we're going to assume that all gases are going to operate the same way by the same principles. We call this an ideal gas. And we're going to look at an ideal gas law that governs this. But first, let's just understand the variables that affect that gas. First off, obviously, it's going to depend on the sheer amount of gas. And when I say amount of gas, what I really mean is the number of particles. We're going to represent that with a lowercase n for number of particles. Okay? What else? Well, the volume of the container, because a gas is going to spread out. It doesn't have a fixed shape, and it doesn't have a fixed volume. So if I were to take all the gas in this room, in my entire apartment, and I was to shove it inside of a little tin can, I could fit all of it, but it would change the properties of that gas. Doesn't matter which gas I'm dealing with, whether it's chlorine, oxygen, hydrogen, anything. As if it's a gas and I take all of it and shove it into a smaller container, it's going to affect the properties in a very similar way. So we've got volume of that gas, and we're going to represent that with a capital V. Next, we have pressure. What is pressure? Well, pressure, we're going to represent that with a capital P. Pressure is going to be equal to the force of something over an area. Okay? It's over an area. So a good example of that is if I take my hand and I push my hand down. Well, that's a force over a certain area. I could take my finger, and that's going to be a much smaller area, this versus this, and press down with the same force. I can feel that more in my hand when I press down with my finger as opposed with my entire hand. I can feel this is very spread out, this is very pointed. So pressure, that force over an area, that's really going to play a part in a gas because we have all of these little particles bouncing around. Imagine it this way. I've got a bunch of little molecules just floating through the air. This is my gas. All of these molecules are moving at a certain velocity. And let's say some of them will hit the wall and bounce off of it. Every time they hit the wall, that applies a force. So it's just like, just imagine, that's a force. I just applied a force. So that force is going to be dependent on the area because the more area I have, the more interactions I can have with that gas, assuming the amount of that gas stays the same over that area. So if I pump a lot more gas in there, if I've got a lot more of these molecules to bounce off, well, I'm going to increase my pressure. So when I say the pressure of a gas, I really mean how much force is that gas applying on the walls of its container. Okay? So we've got pressure. And this should be a concept that we're somewhat familiar with. If you've ever flown in an airplane, the pressure gets different. You can feel it on your ears. If you've ever swam to the bottom of a very deep swimming pool, you can feel the pressure of the water on all sides. It's the force of that water because it's heavy. As you get further down, you're pushing that water out of the way and it's pushing back on you. And it's going to apply over the area of your entire body. So the pressure should be something that we've encountered before. The last factor is going to be the temperature. Temperature, we're going to represent this with a capital T. So these variables should be straightforward. NVPT. All right. But what is temperature? Temperature is explained by the kinetic theory of matter. The idea here is that matter never really stops moving. At the molecular scale, at the atomic level, all of these atoms, all of these elements are moving around. Even in a solid, even if I have these molecules, rigidly connected together by their intermolecular forces, they're still kind of vibrating within those bonds. So they're moving around. They're moving with a certain velocity, with a certain speed. Well, in a gas, that's going to play a huge part. So think of it this way. The hotter the gas is, the more these molecules are going to be moving around, right? If this gas has a temperature of, let's say, 1,000 degrees Celsius versus this one at 100 degrees Celsius, what that means is the molecules of this gas are going to be moving around a lot more, with a lot more velocity. And so I'm going to represent that with longer arrows. So if these gases, if these molecules are hitting the sides of this container with a much larger velocity or speed than these ones, is going to be a lower velocity. Imagine that. Imagine how that would affect the different variables here. Imagine my hand hitting my other hand just like versus, it's going to make a big difference in these other variables. So what we're really going to see is that these variables actually all impact each other. These four properties of a gas, these are the four physical properties of a gas. Now, amount of gas is barely a property, but we're still going to treat it like one. These four are really going to impact each other, okay? So, we need to understand temperature a little bit more because degrees Celsius is a relative scale. What is 0 degrees Celsius? Well, that's the freezing point of water. So 0 degrees Celsius, and then 100 degrees Celsius. So Celsius is based on the freezing and boiling point of water. But we can have negative degrees Celsius. How do you think that's going to impact these gases in our gas law. Well, that's not going to work very well. The problem is that if I can have a negative number, I can't really track very well how that's going to impact my other variables. I need an absolute scale for temperature. And if temperature is just a measure of how much these things are moving around, then I need a place on that temperature scale where these things aren't moving at all. So we have a temperature scale for that. Degrees Celsius is what's commonly used in the SI fundamental system, but they have another temperature scale, and that's degrees Kelvin. So Kelvin, so we call it absolute zero. When there is absolutely no motion, that is 0 degrees Kelvin. Now when we write degrees Celsius, we put this little degree sign. When we write Kelvin, we just put a K. No degrees, no funny business, just a K, capital K. So 0 degrees Kelvin is going to be equal to negative 273 degrees Celsius. That's the difference in these temperatures. So really, the freezing point of water is actually 273 Kelvin. The boiling point of water, well, that would be 273 plus another 100, that's 373 Kelvin. All right. So those are the variables that we need to know. Using that, you should be able to answer the questions on this first sheet. If you have any questions, let me know.